Today, we embark on one of the most fascinating science stories of 2025, 3I Atlas, a traveler from the vast emptiness between the stars. Discovered only months ago by the Atlas telescope, this object immediately ignited heated debates. Is it just an ordinary comet? Or does it carry some kind of message from the distant cosmos? With its hyperbolic orbit proving it does not belong to our solar system. 3I Atlas stands as living evidence that we are not alone in the galactic flow of matter. In our journey today, we will explore its discovery, its strange orbital path, the unusual features of its structure, the scientific controversies it has sparked, and finally, the broader meaning this interstellar visitor leaves behind. On July 1, 2025, at the Cerro Tololo Observatory in Chile, the Atlas system, Asteroid Terrestrial Impact Last Alert System, detected a faint object moving swiftly across the starry sky. At first it was designated only as C-2025 N1 Atlas, just one of the countless new comets discovered each year. But from the very first measurements, astronomers noticed something unusual. The path of this object did not resemble that of any ordinary comet in the solar system. Instead of following an elliptical orbit around the Sun, it traced a hyperbolic curve, clear evidence that it came from interstellar space. This discovery immediately drew the attention of the international scientific community. Before 3I Atlas, humanity had only known of two other interstellar objects, 1I Oumuamua, discovered in 2017, and 2I Borisov in 2019. The arrival of 3I Atlas, exactly the official name later given by the International Astronomical Union, IAU, ushered us into a remarkable era. 3 interstellar visitors observed within less than a decade. Reports in Nature and Science soon confirmed the reliability of the data. The Atlas team announced an orbital eccentricity greater than 1, specifically around 1.025, well beyond the threshold that separates bound orbits from open ones. In other words, the Sun's gravity cannot capture 3I Atlas. It is merely passing through and will leave forever. What drew even more attention was the rapid brightening of the object. Images from the Pan-STARRS telescope, and later the Hubble Space Telescope, showed that 3I Atlas had already begun forming a coma, the cloud of gas and dust surrounding a comet's nucleus even while it was still far from the Sun. Such early and intense activity often suggests that the comet contains abundant volatile substances, potentially very different from comets native to the inner solar system, which are already accustomed to the Sun's environment. Global media quickly covered the story. The New York Times ran the headline, "A visitor from Interstellar. Spacer new comet could change how we see the universe." Meanwhile, The Guardian emphasized the surprise factor. Humanity once again visited by a galactic traveler. Just 6 years after Borisov. These headlines not only captured public curiosity, but also reflected the excitement within the scientific community. Major observatories rushed to schedule follow-up observations. The Subaru telescope in Hawaii, the Very Large Telescope VLT in Chile, and even the James Webb Space Telescope JWST were brought into play. Each instrument offered a different perspective: spectroscopy to identify gases, high-resolution imaging to reveal coma structure, and infrared studies to measure sublimating ice. All efforts aimed at answering one key question: what exactly is 3I Atlas? Timing made the discovery even more special. When Atlas first detected the object, it was still approaching the Sun, expected to reach perihelion in early 2026. This provided a golden opportunity. For months, scientists could observe its journey deeper into the solar system, unlike our moon, which vanished too quickly after its discovery. Research teams immediately began comparing 3.1 ATLAs with its two predecessors. Oumuamua, with its elongated shape and bizarre trajectory, once sparked speculation about being an alien spacecraft. Borisov looked like a typical comet, but contained unusually high levels of CO3I. Atlas appeared to combine both aspects, clearly cometary in behavior, yet showing strange features never seen before. The public was equally captivated. Amateur astronomy forums lit up with discussions. Images of a messenger from the cosmos spread rapidly on social media. On TikTok and YouTube, short explanatory videos about 3IATLAS drew millions of views, demonstrating the power of science to ignite human imagination. Alongside excitement came concern. Some asked, could 3IATLAS collide with Earth? NASA and ESA were quick to reassure. Orbital calculations showed it would not come anywhere near Earth, remaining farther out than Mars's orbit throughout its passage. Still, its appearance was a reminder that the cosmos can always surprise us. By late July, the first detailed analyses emerged. A team at Harvard University reported that the trajectory of 3I Atlas suggested it may have wandered through interstellar space for millions, perhaps billions of years before randomly intersecting the solar system. Its existence became vivid proof that debris from other star systems often drifts across the galaxy and, sometimes, it passes close by us. Against this backdrop, a philosophical question arose. Is 3IATLAS just another comet? Or does it carry with it some kind of message from the cosmos? While symbolic in nature, that question captured the imagination of millions. And to answer it, we must look deeper into the unique scientific traits it reveals. The realization that 3I Atlas was not bound to the Sun immediately shifted the discussion toward its trajectory. Astronomers had confirmed that its eccentricity was well above 1, the mathematical threshold that separates elliptical or parabolic orbits from hyperbolic ones. A hyperbolic orbit means that this object does not belong to our solar system. It did not form here, and the Sun cannot capture it. It is, in every sense, a true interstellar visitor. The trajectory plots, released by the Minor Planet Center in July 2025, illustrated this point vividly. The path of 3I Atlas approached the inner solar system from a direction slightly above the plane of the planets, swinging around the Sun in early 2026 and then arcing away forever. Its incoming velocity relative to the Sun, the excess hyperbolic speed, was calculated at around 26 kilometers per second, a value too high to be accounted for by any gravitational slingshot within the solar system. That speed alone confirmed its birthplace was elsewhere in the galaxy. For the public, the term hyperbolic orbit may sound abstract, but to astronomers, it is the signature of cosmic exile. A comet or asteroid on such a path is a wanderer, cast out from its native star system and set adrift across interstellar space. Theories suggest this ejection occurs when a giant planet, forming in a distant system, perturbs smaller icy bodies and flings them outward with enough velocity to escape their star's gravity. Over millions or billions of years, those fragments drift silently through the void until, by sheer chance, they encounter another star. like ours, the first of these to be spotted, Oumuamua, in 2017, startled scientists with its cigar-like shape and strange acceleration. 2 years later, Borisov behaved more like a classic comet, but revealed unusual chemistry. Now 3I Atlas added a third data point. With each discovery, the case grows stronger that our solar system is not an isolated cradle of debris, but part of a galactic network of wandering objects. Detailed orbital modeling quickly showed just how alien this comet truly is. Its incoming trajectory pointed roughly toward the constellation Hercules, though pinpointing an exact origin star is almost impossible. The galaxy is dynamic. Stars move, spiral around the Milky Way, and carry their debris fields with them. By the time 3I Atlas reached us, its parent star system could have drifted hundreds of light years away. The best astronomers can do is estimate a probable region of origin, perhaps a nearby stellar nursery, or a system with giant planets that could have expelled such a body. What caught attention next was how close the comet would come to the planets of our solar system. Calculations by NASA's Jet Propulsion Laboratory indicated that in early October 2025, 3I Atlas would pass near Mars, at a distance of a few tens of millions of kilometers. While far from any collision risk, this flyby presented a tantalizing opportunity. Spacecraft orbiting Mars, including MAVEN and the European Trace Gas Orbiter, might catch glimpses of the comet's evolving coma and tail. For planetary scientists, this was a rare alignment, a chance to watch an interstellar comet from multiple vantage points. The hyperbolic path also stirred discussions about planetary defense. If an interstellar body were ever on a collision course with Earth, the challenge of deflection would be immense. Such objects arrive with tremendous velocity, giving little warning time and leaving limited options for intervention. While 3I Atlas posed no danger, its arrival reminded agencies like NASA and ESA, investment in early detection systems is critical. Programs such as Atlas itself, along with Pan-STARRS and the upcoming Vera Rubin Observatory, were designed to find these visitors before they surprise us. Beyond practical concerns, the orbit of 3I Atlas raised deeper questions. Some researchers noted that its inclination, the angle of its trajectory relative to the solar system's plane, was moderately tilted, not extreme. This detail suggests that the processes ejecting such objects may be common and produce orbits that scatter in many directions. If we have already spotted 3 in less than a decade, the galaxy may be teeming with them. Perhaps interstellar comets are not rare anomalies, but rather abundant messengers drifting unseen in the darkness. For cosmologists, the hyperbolic orbit is not just a matter of celestial mechanics. It is a narrative thread connecting solar systems across the Milky Way. Each interstellar comet is like a bottled message tossed into the galactic ocean, carrying chemical fingerprints of its home. To catch one, even fleetingly, is to intercept a story billions of years in the making. Journalists seized on this poetic angle. Scientific American described 3I Atlas as a wanderer that writes its path across our sky before fading forever. Le Monde compared its trajectory to a stranger crossing a city street, never to return, yet leaving everyone glancing after in curiosity. These metaphors resonated because they bridged the gap between cold orbital numbers and the human sense of transience. And yet, the orbit remains an anchor. No matter how much mystery surrounds 3I Atlas, the hyperbolic trajectory is the empirical truth that grounds speculation. It is the clearest evidence that this comet does not belong here, that it is a visitor from beyond. As it hurtles toward the sun, the shape of its path reminds us that the solar system is not a closed world, but a crossroads, and sometimes, across that crossroads, strangers pass. The next phase of the story, then, is not just about where 3IATLAS came from, but what it looks like up close. Already, telescopes have captured hints of its coma expanding, its gases shimmering in sunlight, its dust trailing behind like a cosmic veil. To understand its nature fully, astronomers turned their instruments toward the comet's form and activity. The clues written not in its orbit, but in its very substance. As astronomers continued to refine the orbit of 3IATLAS, attention shifted toward its physical nature, what it looks like, how it behaves, and what secrets it carries from its birthplace among the stars. Telescopic imaging quickly confirmed that 3IATLAS was not inert. Even at distances beyond 3 astronomical units, nearly 450 million kilometers from the Sun, it had already begun shedding gases and dust, forming a visible coma. This early onset of activity intrigued researchers because it implied that highly volatile compounds, such as carbon dioxide or carbon monoxide ice, were abundant within the nucleus. The Hubble Space Telescope provided the first detailed images, showing a coma spanning tens of thousands of kilometers. Unlike the diffuse halos of many solar system comets, 3.1 displayed an asymmetric plume pointing sunward, a curious reversal of the classic cometary tail that normally streams away from the Sun. This feature suggested jets of gas were erupting from beneath its crust, creating a localized outflow strong enough to shape the coma in unusual ways. Spectroscopic studies soon followed, using the Very Large Telescope in Chile and the James Webb Space Telescope in orbit. Teams detected emissions from water vapor, carbon dioxide, and traces of more complex molecules. Interestingly, the CO's signature was disproportionately strong compared to water, echoing what had been seen in 2I, Borisov, but at even higher levels. This chemical profile raised questions about whether interstellar comets form in colder, more distant regions of their parent systems than most solar comets, or whether their surfaces preserve a more pristine record of early stellar chemistry. Another peculiar aspect was the dust production rate. Pan-STARRS and Subaru data indicated that 3I Atlas was shedding dust at a rate equivalent to hundreds of kilograms per second, producing a broad tail visible in stacked long-exposure images. Yet, the dust grains appeared unusually large and reflective, giving the comet an unexpectedly bright magnitude for its size. Some scientists speculated that the nucleus itself could be small, perhaps just a few kilometers wide, but cloaked by an exaggerated dust halo that amplified its visual presence. The sunward plume drew further scrutiny. Was this simply a jet created by uneven heating, or did it signal something more exotic about the comet's composition or internal structure? A few fringe interpretations suggested that directional out could resemble controlled thrust, reminiscent of the debates that followed Oumuamura's strange acceleration in 2017. While mainstream astronomers cautioned against speculative leaps, they admitted that interstellar objects often defy expectations, and careful observation was essential before ruling anything out. By late August 2025, coordinated campaigns between professional observatories and skilled amateur astronomers were underway. Backyard telescopes across Europe, North America, and Asia began to capture the comet as a faint greenish smear in the night sky, with its head distinctly glowing. The green coloration was consistent with diatomic carbon C emissions, a hallmark of many comets but now seen in an interstellar specimen for the first time in detail. This provided yet another piece of the puzzle. 3I Atlas was chemically active. Not just a sterile rock. Radio observatories joined the effort as well. The Atacama Large Millimeter Submillimeter Array, ALMA, detected rotational transitions of specific molecules, helping to quantify the ratios of carbon-based species. These data, published in Astronomy and Astrophysics, confirmed that the comet's gas inventory deviated significantly from the average composition of known solar comets. In particular, its relative scarcity of ammonia hinted that it may have formed in a nitrogen-poor environment, perhaps in the outer regions of a star system with very different initial conditions than ours. For planetary scientists, the morphology of 3I Atlas represented a unique opportunity. Its coma and tail were laboratories in motion, revealing information about interstellar chemistry without the need to send a spacecraft across light. Studying the flow of dust and gas provided insights into the mechanical properties of its nucleus. Was it a fragile rubble pile barely held together, or a solid icy body coated with a thin crust? Early models suggested it was fragile, shedding material with ease, consistent with an object that had endured eons of cosmic radiation. The unusual plume, however, remained the most striking feature. NASA's Goddard Space Flight Center compared it to a blowtorch angled toward the sun, a striking description that quickly found its way into headlines. Could it be that interstellar comets behave differently because they store energy in unfamiliar ices, releasing it explosively when warmed? If so, 3I Atlas might help scientists understand not just the diversity of planetary systems, but the chemistry of star-forming regions spread across the Milky Way. For the public, the visual spectacle became a focal point. Renderings based on telescope data circulated widely online, showing the comet's glowing head with a sharp, defiant jet pointing inward toward the sun, while a fainter dust tail streamed outward behind it. It was a mirror-image paradox, as though the comet itself were challenging the laws of cometary physics we thought we understood. And as the comet approached perihelion, activity was only expected to increase. If the unusual gas ratios continued, astronomers might witness outbursts or fragmentation events, violent releases of material that could brighten the comet dramatically. Each flare-up would offer fresh clues to the internal composition of this interstellar nomad. The morphology of 31A TLAS thus became the canvas upon which speculation and science intertwined. Its structure told a story of volatile ices, strange chemistry, and powerful jets. Its activity hinted at processes unfamiliar in solar comets, and every observation reinforced the truth that this object, though only a transient visitor, carried with it a signature of places far beyond our sun by the time 3I Atlas had revealed its peculiar plume and chemistry. The debates began to intensify. Astronomers and planetary scientists were faced with the same haunting question that had accompanied every interstellar visitor so far. Was this just another comet, or something more? The first camp, the cautious majority, argued that 3I Atlas should be interpreted within the framework of cometary science. To them, the strong co-emissions, the asymmetric coma, and the early activity were unusual but not unprecedented. Solar system comets are themselves a diverse population. Some show sunward plumes, others fragment violently, and many have odd compositions. Extending that diversity to interstellar objects made sense. A comet born in a different star system might simply reflect different initial conditions, such as colder formation zones or altered abundances of carbon and nitrogen. Yet others were less satisfied. The hyperbolic trajectory, the exaggerated activity, and the powerful plume seemed to invite bolder speculation. A subset of researchers recalled how Oumuamua's non-gravitational acceleration had been attributed by some, most famously Harvard's Avi Loeb, to the possibility of artificial origin. Although that hypothesis remains controversial, the echoes returned with 3 IATLAS. Could an interstellar object showing directional outgassing also be a probe, or at least carry technological significance? Mainstream journals like Nature, Astronomy urged caution. Editorials emphasized that extraordinary claims require extraordinary evidence, and that no data yet indicated anything beyond natural processes. The sunward jet, while unusual, could be explained by volatile-rich vents or asymmetric surface heating. And unlike Oumuamua, which showed no coma, 3.1 ATLA has clearly behaved like a comet, producing gas and dust in familiar ways. For many, this alone was enough to keep it within the bounds of natural astrophysics. Still, the broader public seized on the mystery. Headlines from The Independent asked, "A message from the cosmos?" while Popular Mechanics ran features about how interstellar comets might be messengers of life. The word message was not meant literally in most cases, but symbolically. The idea that such objects could carry chemical records from other solar systems, potentially even prebiotic molecules. If panspermia, the theory that life's building blocks travel between stars, has merit, then objects like 3I Atlas may be crucial to that cosmic exchange within the scientific community. Several hypotheses crystallized. The pristine relic hypothesis. 3I Atlas is a natural comet, ejected from its parent system early in its history and preserved in deep freeze for billions of years. Its unusual chemistry reflects a star-forming region different from the Sun's, making it a valuable probe of galactic diversity. The exotic ice hypothesis. Its activity might be driven not only by water and sea, but by ices rare in our solar system, such as molecular nitrogen or complex hydrocarbons. This could explain the disproportionate CO signature and the vigorous sunward plume. The fragment hypothesis. Some argued that 3I Atlas could be a shard of a larger parent body, broken off during violent planetary formation events in another system. If so, its irregular structure could create uneven jets, mimicking purposeful thrust. The artificial hypothesis. The most speculative camp suggested that unusual activity might not be natural at all, but indicative of technology, though lacking direct evidence. Advocates pointed to the repeating pattern of strange interstellar visitors, from Oumuamua to 3I ATLAS, as warranting serious consideration. Debates spilled into conferences. At the International Astronomical Union's 2025 symposium, presentations alternated between sober orbital analyses and more daring suggestions. Younger astronomers often pressed for openness to radical ideas, while veterans reminded the community of the risks of sensationalism. The memory of past controversies loomed large, yet so did the thrill of possibly encountering something unprecedented. Interestingly, some astrobiologists found a middle ground. Even if 3I Atlas was entirely natural, it might still carry an implicit message. The molecules it releases into space are signatures of alien chemistry. Comparing them to comets in our own system could reveal whether planetary nurseries across the galaxy share a universal recipe. If amino acids or other organics were detected, that would have profound implications for the likelihood of life elsewhere. NASA and ESA, meanwhile, discussed, at least conceptually, whether rapid response missions to interstellar objects might be possible in the future. While no spacecraft could feasibly reach 3I Atlas in time, the dream of launching interceptors, perhaps staged at the outer solar system, gained momentum. The possibility of sampling an interstellar body directly was described by one scientist as like opening a time capsule from another world. Public fascination grew as speculation swirled. Social media amplified the more dramatic theories, with hashtags like #message from the cosmos trending on TikTok and Twitter. Documentaries began framing the story as a mystery narrative. Was this a frozen relic, a shard of another world, or a deliberate emissary? Though scientists stressed natural explanations, the cultural narrative was already blending science with myth. This tension between caution and curiosity has always defined humanity's relationship with the unknown. When comets blazed across medieval skies, they were omens. When the first telescopes revealed moons and galaxies, they inspired both fear and wonder. Now, in the 21st century, interstellar comets provoke the same duality. They are scientific data points, but also vessels for imagination. By autumn 2025, as 3I Atlas brightened and its plume grew more dramatic, the debates reached a crescendo. Was it ordinary, extraordinary, or something in between? The next stage of inquiry would move beyond hypotheses toward implications. What this visitor means for science, for philosophy, and for our collective sense of place in the cosmos. As 3I Atlas approached perihelion in early CO 2026, its presence in the night sky became more than a scientific curiosity. It was a cultural and philosophical event. Astronomers tracked its every outburst, journalists chronicled its unfolding story, and the public followed with fascination. What did this wandering fragment of another star system truly mean for us? The immediate impact lay in science itself. With each observation, researchers added to a growing library of interstellar object data. From Oumuamua's enigmatic acceleration to Borisov's rich chemistry, and now to 3I Atlas's vigorous activity. A pattern was emerging. Interstellar visitors are not identical, but they are not wholly alien either. They carry echoes of both familiarity and strangeness. For planetary science, this reinforced the idea that our solar system is part of a much larger continuum. Comets, asteroids, and icy bodies are not confined to the Sun's domain, but are ingredients scattered across the Milky Way. The philosophical implications stretched further. To many, 3I Atlas was a reminder of cosmic kinship. Its molecules, CO, water, carbon-based compounds, resonated with the chemistry of life on Earth. The possibility that such objects could ferry organic materials between star systems rekindled debates over panspermia. Even if 3I Atlas carried no life itself, it symbolized the interconnectedness of galactic environments, as if stars shared recipes across light years. For astrobiologists, that was a profound encouragement. Life might not be unique, but seeded widely across the cosmos, politically and strategically. The comet underscored the importance of planetary defense and rapid response technology. Though 3I Atlas posed no danger, its hyperbolic speed highlighted a vulnerability. If one day an interstellar body were on a collision course, Earth would have very little time to prepare. Agencies like NASA, ESA, and JAXA used the comet as a case study, accelerating discussions of how to intercept or at least closely study future visitors. Proposals included pre-positioned spacecraft in the outer solar system, designed to spring toward such objects when detected. A mission like that, while ambitious, could transform science in ways comparable to the Apollo program. For the public 3I Atlas was more than policy or data. It became a mirror reflecting human imagination. Social networks buzzed with images of a cosmic messenger, half poetic. Memes portrayed it as a galactic traveler bearing secrets. Artists painted it as a burning eye streaking across the heavens. Even mainstream outlets leaned into metaphor. The Washington Post described it as a message written in ice, while El País called it the whisper of another world carried on dust. This narrative, half science, half myth, tapped into something timeless. For millennia, comets have symbolized omens and revelations. Now, even with telescopes and spectroscopy, the awe persists. The difference is that we can now translate some of the message. Isotopic ratios, molecular signatures, orbital dynamics. Yet the mystery remains, inviting both rational study and imaginative wonder. Cultural commentators noted how quickly 3IATLAS became part of a broader conversation about humanity's place in the universe. At a moment when Earth faces climate change, geopolitical strain, and rapid technological upheaval, the comet arrived like a reminder of scale. Against the backdrop of billions of years and trillions of kilometers, our disputes seemed small. Interstellar objects embody perspective. They are ancient, rootless, and indifferent to borders. And yet, by studying them, humanity writes itself into the cosmic story. The educational impact was also significant. Schools incorporated 3IATLAS into curricula, museums hosted exhibits, and planetariums staged immersive shows. Children who looked through telescopes to glimpse its faint glow were told they were seeing something that had traveled for millions of years through the galaxy, and that might never happen again in their lifetimes. Such moments inspire generations of scientists. Just as Halley's Comet once fueled imaginations, so too might 3I Atlas ignite the careers of future astronomers and engineers. But what about the message? Was there one at all? Scientifically, the comet was mute, just dust, ice, and gas. Yet symbolically, its message was rich. It said, "You are not alone in material terms. Your solar system is not unique. The same physical processes that shaped Earth and its neighbors are playing out in countless systems." In that sense, the comet is a cosmic reassurance that the universe is not empty, but filled with kin, as it rounded the sun and began its outward escape. Fading back into the abyss, 3IATLAS reminded humanity of impermanence. We had only months to observe it, then it was gone, on a path that would take it forever beyond our reach. The fleeting nature of the encounter became part of its meaning. Opportunities in science and in life are brief, and we must seize them when they arrive. In the end, 3IATLAS was both ordinary and extraordinary. Ordinary because it obeyed the laws of physics, outgassed like a comet, and followed a predictable path. Extraordinary because it was born in another star system, carried alien chemistry, and visited us by cosmic chance. Ordinary because no hidden engines or signals were detected. Extraordinary because its very existence connected us to worlds we will never see. Thus, the comet left behind two legacies. The first was scientific: data, spectra, orbital calculations, a richer understanding of interstellar objects. The second was cultural: inspiration, humility, and wonder. Both are vital. Both remind us that knowledge and imagination walk together. And so, when the comet faded from view, it did not vanish entirely. It lingered in papers, in classrooms, in artworks, and in minds. A messenger not of words, but of presence. It told us that we are part of a larger story, one written not only in the solar system, but across the galaxy itself. The journey of 3i, Atlas, has now passed through the chapters of discovery, orbital revelation, physical character, and scientific debate, leaving us to reflect on its meaning as it fades back into interstellar darkness. Over the course of months, this visitor from beyond became a canvas for both rigorous science and human imagination. It demonstrated the precision of telescopes, the dedication of astronomers, and the power of collective curiosity. More importantly, it reminded us of the vast stage on which our solar system plays only a minor role. We often speak of comets as dirty snowballs or icy relics, but when those relics arrive from another star system, their symbolism transcends the technical. They are time capsules of alien chemistry, fragments of places we may never see, carrying whispers of formation histories utterly different from our own. Whether 3i Atlas was extraordinary or ordinary, its message was clear. The galaxy is alive with exchange. Matter is not locked within borders. Across billions of years, it drifts, collides, and wanders, binding systems together through shared fragments. For humanity, such encounters are invitations. They invite us to ask bigger questions, to plan bolder missions, and to consider our place in the cosmic web. They remind us that while Earth is fragile and temporary, it is also part of something enduring. The fleeting sight of an interstellar comet tells us that we are not isolated. Our solar system is porous, touched by visitors, sending its own debris outward in return. This is both humbling and empowering. When children looked up at 3i Atlas through small telescopes, they were not just seeing a comet. They were glimpsing the connective tissue of the galaxy itself. They were watching proof that the story of our sun and planets is linked to stories written light years away. If there is a message from the cosmos, it is this: we are participants in a shared galactic history, not bystanders. And in embracing that truth, we learn to see ourselves not just as earthlings, but as citizens of a wider universe. So, as 3i Atlas disappears from view, its legacy remains. It carries us forward with questions that stretch across science, philosophy, and imagination. It asks us to prepare, to dream, and above all, to keep looking up. For somewhere in the vast dark, another messenger is already on its way.